Hey guys, so in this video we're going to be looking at the speed of light, and that's actually going to carry us into refraction as well. So first things first, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. Now you may remember that the speed of sound was about 340 meters per second. So this is 3 times 10 to the 8th. So that's a 3 with 8 zeros behind it. That means it's about 1,000,000 times faster than sound. Now, one thing to remember is that this is the speed of light in a vacuum. All right. Now, that's different than sound, right? Because sound required a medium. You needed some type of material, the air or the water or a solid. You needed some type of material for the sound, the vibrations, to hit other molecules to pass that sound on and on and on until it reached your ears. Now, light doesn't need that. Light is an electric and magnetic field that are balancing back and forth, and it doesn't actually need any particles to be able to transmit. In fact, when there are particles, it goes slower because it bounces off of those particles. It kind of changes direction. Sometimes it gets absorbed by those particles, and then it spits them back out. So there's a lot of different things that happen there when light hits particles. And so light actually goes fastest in a vacuum, like when it's going from the sun to Earth. Now, it takes several minutes for the light to get from the sun to Earth. You could do that calculation. You could figure out the distance of the sun from the Earth, and you could calculate about how long it takes for it to get here. But the reality is, if the sun were all of a sudden to disappear, we wouldn't know it for a couple of minutes because the light would still be coming to us, and we wouldn't know until the light stopped arriving. All right. Of course, if the sun just disappeared, there wouldn't be any mass there as well. So gravity would kind of fall apart as well. We'd stop going in a circle around the sun. But with that having been said, let's go ahead and move on. Recognize this is the fastest that light goes. I am mentioning this here. Light does not have mass. It's a wave. So the light itself does not have mass. That's one reason why it doesn't require a medium, because it's not particles moving. It's just this energy wave moving through space. All right. Now, one of the questions that I wanted to look at, and that people sometimes ask, is they say, well, temperature affects the speed of sound, right? As you make the air hotter, the molecules move faster, so sound moves faster, and it causes it to spread out more and bend and all the other things that we talked about in the previous unit. However, light doesn't require a medium. So does temperature affect the speed of light? And the answer is no. The temperature doesn't affect the speed of light. Temperature might affect a medium if light is traveling through air, or if light's traveling through a solid or something like that, then it could affect that medium. But as far as the light is concerned, making it hotter or colder won't make the light travel faster or slower. All right. Now, one thing that does happen is that light can be affected by the temperature in this way. You'll notice in my flame over there on the left that the bluest part of the flame is down at the bottom of the candle, right? The bluest part of the flame is down the candle. That's where it's hottest. The white or the yellow or the red is kind of on the outside of the flame. Remember, white is the combination of all the colors. So in the middle is all the colors coming out. On the edge, when it's actually the coolest, because we're furthest away from where it's actually burning, that's red. And the part in the center where it's the hottest, that's blue. Now, that should kind of correlate with what we understand with the colors of light. So that should kind of correlate with what we know about the colors of light. Remember this up here, this Roy G. Biv thing? Remember, red light is the least energetic. It's the light that has the least energy out of all the wavelengths of visible light. Violet or purple or blue has the highest energy. And so that's an important idea in recognizing that the hottest things are going to be blue. Does that affect the speed? No. Remember, the speed of all light is the same. What's different is just the color. We see this actually in this graph over here on the right. is that we see that as something gets hotter, it's not that it doesn't show any other colors, it's just that the peak of that wave moves more and more towards the blue side. If you look right here at this wave that is 3,500 Kelvin, right? The peak of that wave is up near about 700 or 800, which means you're getting a lot of red. Remember, red wavelengths were up in the 700 nanometers. So you got the red up there. You've got the even infrared up there. All right. Remember, not visible light, but that's the next lowest. As you get longer wavelengths, you have longer wavelength means less frequency, which means less energy. So you're getting more red over there. As we get the light hotter and hotter, as whatever it is creating the light is hotter and hotter, then we start to get higher temperatures. And as you get higher temperatures, then the average energy of that light shifts over to the left in our picture here. And so as it's shifting over to the left, you can see that the peak, the light that's being shined most often, is less red and less red and less red. All right. In the center here, you see the 5000K, which is centered pretty closely between your 300 and your 700. Those are the colors that we were kind of looking at, those wavelengths. And so we have 5000, which is all yellow now. So you can see that the colors are going to be different based off of the temperature. All right, now all this stuff leads us into refraction. Because we talked about a little bit at the beginning that as light goes into a different medium, because there are particles there reflecting, absorbing, transmitting the light may travel through a little bit slower. This causes refraction. Now, we learned about refraction with sound. Remember, we said that sound, when it went from one medium to another, it could cause it to bend. You watch the video about when it's nighttime, as the temperature of the air changes, it causes the sound to bend and curve back down to the earth. So some interesting things there with the bending of waves. Well, this is one of the evidences that light is a wave. And some of you ask that question, well, how do we even know that light is a wave if we can't see the particles moving? How do we know? Well, one of the reasons we know is because it has wave properties. One of those wave properties is refraction, and the light bends. And you've seen this. We used this as an example earlier. We talked about the straw in the glass and how you look at the straw in the glass and it looks like the straw has been moved over and maybe it's a little bit bigger. It's been bent. It's not because the straw is there. It's just because the way that the light is moving through the water in the glass is different than the way that the light is moving through the air. You can even see the bend right here a little bit. We usually talk about this part right here where it looks like the straw is broken. But look right here when we go from the air to the light passing through the glass. Even the glass, which is clear, causes a little bit of the bending of the light. And you can tell that the straw bends a little bit there. This happens because the speed of the light is changing. It needs to maintain its frequency. And so in order to maintain its frequency, it has to get through a certain distance in less time. We're not going to worry too much about the why. Just recognize that it's happening. We see the light bending. This also explains why you see mirages out in the desert. When it's hotter down near the surface, then the light is going to bend because of the air being different down there, and it's going to cause the light to reflect and bend in different ways that causes you to see the water on the surface, either out in the desert or on the surface of the road. This is due to this idea of refraction and the light changing speed as the medium changes, right? All right, so I want to show you one more demo. This is something that it will be an option for your lab, one of your labs. Remember, you have to do 2 labs in this unit. And so I'm going to talk you through and show you one more example of refraction and how we can actually measure it. All right, so come with me. Let's check out the lab. All right, guys, so I'm going to show you now an introduction to the Acrylic Lab, but also just to kind of demonstrate this idea of the bending of light. Okay, now to do this, I have a block of acrylic, and I've traced it on my paper so that even when I've removed the acrylic, I'll be able to see it. Okay, And then I've got a nice little laser here. I got a purple laser, fun, fun, fun. And then I've got a bunch of pins that are going to help us locate different places. Okay, now I'm going to do my best to keep my laser in the same place right here throughout the rest of the video. Now you can actually see pretty well what's happening as the light passes through. You can see the light going from the laser here. It's going through the glass, and then it's coming out the other side. All right, now the first thing I want to do is I'm going to mark this light that's passing through. Okay, so I'm going to put a pin over here at the end. I'm going to start furthest away, and I'm going to work towards the light, because as soon as I put something in front of the light, it's going to block most of the rest of the light, and you're going to not be able to see it very well. So I'm going to start far away. So we're going to start, let's see, again, I want to make sure that I'm keeping this in the same place, hopefully, the whole time. So I've got one light right there, okay, and then I'm going to put one right here where it's coming out of the glass, so right there. I'm going to put another one in where it's going into the glass right here. So I'm watching the laser. I'm putting my pin just so that I can see the light go into the laser right there. I'm going to put it right there. Okay, and you can actually see where it's bouncing off of the pin there. And then last of all, sorry, I want to make sure that this is still in the right place. Last of all, I'm going to go ahead and put a pin right in front of the laser there. Okay, now there's a couple other things that I want to mark. Unfortunately, I'm going to need to remove this just for a minute. I want to see this laser right here, okay, that light. So this is the laser coming in and reflecting off the surface there. And then also, you may be able to see this one, right? As the laser comes in, it then goes through the glass, and then actually on the inside of the glass, it's bouncing off over here as well. All right, and so as best I can, I want to kind of try to mark that spot. That one's a little bit harder to see, but the fact that it's bouncing off there is an important idea. And then I will replace this one right here, right in front of my laser. All right, perfect. So now I've got all those places marked. So what I'm going to do at this point is I'm actually going to remove the glass, the acrylic here, and we're going to trace each of these lines. Okay, so as I go, I'll remove the pins. So the light's coming in like this, and then it went through the acrylic, and you'll see that in order to go through the acrylic, it's going to have to bend a little bit, like this. All right, so note that inside of the glass it's going in a straight line. It's only right here at the surface. In some languages, they don't actually use the word bend. They don't say the light bends, they say the light breaks, because at this point there's kind of a break that it actually changes immediately there. And then I'm going to go ahead and draw this one right over here, just like that. Okay, now we noticed a couple other things. We saw the light reflecting over here, so we'll go ahead and draw that one in. And then we also saw the light reflecting over here, and so we'll draw that one in. And at this point we expect it would have left, but by that time the light was pretty dim and I wasn't able to get that. All right, so we got a pretty good drawing here of what the light was doing. All right, I've drawn in what we call the normal, the perpendicular to the surface on both of these surfaces where the light was hitting. I want you to notice a couple of things. The first thing I want you to notice is that as the light comes in, it comes in at a certain angle, and then it reflects, and it reflects off at essentially the same angle. Now, if it's not the same, it's my fault. It's not the fault of the light. But this is what's called the law of reflection. The law of reflection says that whatever angle the light hits at, this angle with respect to the normal, is the same angle with which it's going to reflect. And we see the same thing down here. The light comes in, and it reflects off the surface. So it doesn't matter if we're outside in the air or if we're inside in the glass. When we change surfaces, some of that light is going to reflect. Now, that is one of the properties of waves, right? Is waves reflect. We talked about that with sound as well, that sound reflects. We get echoes and things like that. And so that's a significant part of light. But what we really are looking at here is that idea of the bending of the light. All right. Now I'm going to introduce you to two formulas here. The first one is up here. N equals C over V. Now N is something we call the index of refraction. And all objects have an index, all materials have an index of refraction for light. Okay? The C at the top is the speed of light in a vacuum. So that's that 3 times 10 to the 8th meters per second that we saw previously in the video. The V is the speed of light in this material. So for example, acrylic has a very specific index of refraction, and it compares the speed of light in a vacuum to the speed inside of the acrylic. Now, inside of the acrylic, we know it should be going slower. So one of the things that we notice is that as the light comes into the acrylic, if it goes slower, then it's going to have a smaller angle here. That angle is going to get a little bit smaller. All right. Now, that leads us into our second equation here, which is that the index of refraction of your first material times the angle in that material should be equal to the index of refraction in your second material multiplied by the sine of the angle in that second material. And I do want to show that to you right here, and I'll show you that it works. It'll be close. Again, we are taking real data, and there's a chance that I made a mistake on my measuring of the angles or something like that, but let's go ahead and see if that works. Now, one of the things that you should know is that the index of refraction of air is really, really close to 1. Okay? Even though there are particles in the air, the light pretty much just passes through it, almost as if it were the speed of light. Now, really, it's like 1.00 something, but it's close enough to 1 that we're going to go ahead and assume that it's 1. Now, looking at our formula for index of refraction, if the index of refraction is 1, then that means it's the speed of light divided by the speed in the air, and so the speed in the air is approximately equal to the speed of light. That way, when we divide these numbers, we get a value of 1. So in the air, it's 1. However, in the glass, because we see a smaller angle here, we do know that the speed of the light in that acrylic is going to be a little bit less. All right? And we're going to actually figure out what that speed is by using the data that we have here. The first thing that we're going to do is we need to find out what the index of refraction in the acrylic is. All right? So we're going to do that by using this second equation right here. So you'll see right here as it goes in from the air. So the air is going to be medium 1. So I'm going to put 1 for my index of refraction 1. And then I'm going to multiply by the sine of the angle that we get going in the air. So I'm going to use my protractor here, and we're going to measure that angle right there. We're going to make sure that this baseline measures up with the side of our block there. Okay, the 90 should be right on my perpendicular line there. And I get that from here, I am measuring from this line to the middle. So from the baseline to there is 50, which means from here over there, that needs to be 10, 20, 30, 40 degrees. All right, so that right there is 40 degrees. So I'm going to put sine of 40 here. Then that's going to be equal to the index of refraction in the second material, which is my acrylic, times the sine of theta 2. Now theta 2 I can measure over on the other side here. So we're going to put the protractor right there. And we notice that it goes from 90 over to about 67 there. So that would be 10, 20, 21, 22, about 23 degrees. So 23, just like that. And so now I should be able to put that into my calculator here. So I'm going to do sine of 40. All right, I'll hold this up so you can see it. So the sine of 40 is 0.643. So we'll go 0.643 times 1, it'll be 0.643, equals index of refraction 2 times sine of 23. So we'll go sine of 23 there and we get 0.391. So 0.391. Now to solve for the index of refraction, I'm just going to take that 0.643 and we're going to divide by the answer that we just got, that 0.391. And I get an answer of 1.64. All right, so that is the index of refraction of the acrylic. Now, I'm only going to do it once, but when you do your lab, you're going to do that a couple of times, right? We always want to make sure that we do multiple data points because this answer could be off based off of my drawing and human error and things like that we've talked about before. So multiple times, we'll get an average index of refraction. And then we're going to go ahead and we're going to use that in this top equation to find out how fast my laser light is actually moving in the acrylic. And so to do that, we're going to take the index of refraction, which is, so we're going to take this N equals C over V. So N is going to be 1.64, which is going to be equal to the speed of sound, the speed of light in a vacuum. So 3 times 10 to the 8th meters per second divided by V. So I'm going to multiply both sides by V. One of the things that hopefully you learned in algebra is that if you have the variable on the bottom, you got to get it off the bottom first. So I'll multiply both sides by V. That'll get rid of this. And then I should be able to divide by the 1.64. And so to get my answer, I'm going to take 3 times 10 to the 8th power. And then I'm going to divide that by the 1.64. And I get a final answer of big number. Notice that it's still 1, 2, 3, 4, 5, 6, 7, 8 spaces over. So 1.83 times 10 to the 8th power. So the speed of this light in acrylic is about 1.83 times 10 to the 8th meters per second. And so it's a little bit slower, right? Almost half the speed of light in a vacuum, but still pretty darn fast. One thing to recognize is that I used a purple laser. Different color lasers will actually end up giving you slightly different indexes of refraction and therefore slightly different speeds. All right, but hopefully you're recognizing here that we see the bending of the light, we see the refraction, we see the reflection, and those are all things that are properties of waves, which gives us a pretty good indication of the fact that light is acting like a wave. That's the end of this video.